Welcome to The Explainer. Today, we're diving into a really cool topic, the phantom forces of a rotating world. It's all about rotational dynamics, and we're going to break it down step by step.
Okay, think back to being on a merry-go-round. You feel that pull, right? The one that feels like it's trying to fling you outwards. And if you ever tried to walk a straight line on one, you know something feels like it's pushing you sideways. Well, that's not just in your head. It's real, it's physics, and it's exactly what we're talking about today.
So, to really get a handle on this, we're going to tackle a classic problem from Irodov's Problems in General Physics. Think of this problem as our own little physics lab. It's the perfect setup to see these invisible pushes and pulls in action. So here's the full problem. We've got a flat disk, and it's spinning at a constant speed. Now, imagine a little puck sliding along a line drawn right across the diameter of that disk. It's moving at a steady speed relative to the disk. The question is, what is the total force that the disk itself has to exert on that puck to make all of this happen? First things first, like with any physics problem, let's get organized. We'll list out everything we know. We've got the angular velocity, the mass of our little body, its velocity relative to the disk, and its exact position from the center at the moment we care about. All our ducks are in a row. All right, now this is the point where a lot of people make their first mistake. It's really tempting to just look at this problem and think it's simpler than it is. This is a classic trap in rotational dynamics. So let's try to put ourselves on the disk. Imagine you're a tiny observer spinning around with it, watching this puck slide past. From your point of view, what forces do you think the disk is applying to it? Your first thought is probably the obvious stuff, right? There's a normal force pushing up, fighting gravity, and maybe some friction to keep it moving. But that can't be everything, because if you were watching this from a stationary spot above the disk, the puck's actual path isn't a straight line, it's a spiral. So there's gotta be more going on. Something really important is missing from this picture. And here it is. This is the aha moment. To solve this correctly, we have to completely change our perspective. We have to do our analysis from inside the rotating system. You see, our spinning disk is what physicists call a non-inertial reference frame. All that means is that it's accelerating, in this case by rotating. And in an accelerating frame, Newton's simple F equals ma law doesn't quite work on its own. To make the physics make sense from inside the spinning disk, we have to introduce a couple of new players. We call them fictitious forces. Now, they're not imaginary. Their effects are very real. They're more like corrections you have to make because your point of view is moving in a complicated way. And this really shows the difference. If you're on the ground, in an inertial frame, Newton's laws are simple, but the path of the object is really complex. But if you switch to the non-inertial frame of the disk, the path is simple, just a straight line, but you have to add these new fictitious forces to make the laws of motion work. It's a trade-off that makes solving the problem way easier. Okay. So let's properly introduce these two phantom forces that are the absolute heroes of our story today, the centrifugal force and the Coriolis force. First up is the centrifugal force. This is the one you're already familiar with. It's that outward pull you feel on the merry-go-round. From the disk's point of view, this force is pulling our little puck straight out, away from the center of rotation. And then there's the Coriolis force. This one is a little bit stranger. It only pops up when an object is moving within the rotating frame, and it acts sideways, perpendicular to the direction the object is moving. This is that weird sideways push you feel when you try to walk on the merry-go-round. And in our problem, this is the force that's trying to knock our puck off its straight line path. All right. We have the concepts, we have the players, we have the formulas. Now it's time to put it all together and actually calculate the force. Okay, so here's the logic. From the disk's point of view, the puck is moving at a constant velocity. That means its acceleration relative to the disk is zero, so the net force must be zero. This means that the real physical force the disk exerts has to perfectly cancel out all the other forces acting on the puck, and that includes our two phantom forces. We can break this real force down into three parts that do just that. Let's start with the easy one, the vertical force. The disk has to push up on the body to counteract gravity. That's just the normal force, which is equal to the body's weight. Simple enough. We calculate that to be 4.9 newtons. Next up, the radial force. The centrifugal force is trying to fling the puck outwards. We calculate that force to be 5.4 newtons. So, for the puck to stay on its path, the disk must exert an equal and opposite force, pulling it inward with 5.4 newtons of force.
And finally, we have the tangential force. As the puck moves outward, the Coriolis force is trying to push it sideways. We run the numbers and find that force is 3.0 newtons. So to keep the puck moving in a perfectly straight line, the disk has to push back sideways in the other direction with an equal force of 3.0 newtons.
So let's take a quick look at what we've got. The disk is pushing upwards, inwards, and sideways, all at the same time. We have 3 distinct force components, and the cool thing is they're all at right angles to each other. So how do we combine these 3 perpendicular forces into one single total force? Well, we use the 3D version of the Pythagorean theorem. Think of the forces as the length, width, and height of a box. The total force is just the length of the diagonal that cuts through that box. We plug in our numbers, 4.9 squared plus 5.4 squared plus 3.0 squared. We add them up, take the square root, and we get our final answer. The total force that the disk exerts on the body is 8.0 newtons. And that's it. Problem solved. So we solved the problem, we got the number, but what's the big lesson here? What should you really take away from all of this? It all comes down to this. When you are analyzing motion from inside a rotating system, you absolutely, positively have to account for the centrifugal and Coriolis forces. They might have the word fictitious attached to them, but if you ignore them, you will get the wrong answer every single time. And that leaves us with one last really big idea. Our entire planet is a giant rotating reference frame, and that same Coriolis force that we just used to solve a textbook problem, that's the exact same force that causes massive air currents to curve, creating the spin of hurricanes. So I'll leave you with this thought. How fictitious can a force really be if it's powerful enough to shape the weather for our entire world?